When I'm graduating.
Is it this spring or?
No, I still got it. Thank you.
Dr. Stevens, 8 o'clock. Okay. Oh, good morning, folks. Thank you for being here. Remember that we have an exam this Friday. Setting up the practice exam to be online using the Proctorio proctoring service is becoming more of a hassle. I was assured that they would, the ITRC would have that up and ready today, but it is not. Hopefully that will occur later today. So, but in any case, I have posted a PDF file of the practice exam as well as solutions you can check. And once the practice exam is available as an online quiz that you can take via Proctorio, I would encourage you to try it just to make sure that you can get the software to work on your computer. Again, you'll have to use the Chrome browser and you'll have to download special software. In fact, you could do that already off of the Moodle website just by reading through the documentation there that's at the very top of the page. And under the Proctorio link, you can download the software there. So this came up in a question earlier today, in that the final exam will cover material that is not on this exam on Friday, in that we will be covering new material next week. And hopefully it won't take both lecture days. So I'd like to spend at least half of the last day of class doing kind of an overview review of what I think is important over the semester. But a good chunk of the final will be on the new material that we have yet to cover. So where we left off yesterday was talking about, the recent advances over the last 150 years or so, and how that really changed things. And especially in the early 1900s, the rate of the change in our understanding was incredible. And a lot of people had difficulty keeping up with it, but it was also a very exciting time. So something that happened in the late 1800s is, with all the new technology advances in electricity, people were playing around with lots of different devices, trying to invent a light bulb, amongst other things, where they were dealing with basically evacuated spaces, high voltages, that sort of thing. And one thing that was developed is called a cathode ray tube. And I had one of these in class to demonstrate the deflection of an electron beam. I'm pretty sure all of you remember that. And that's a cathode ray tube. In fact, the electrons, what we now call electrons, when they first noticed this, they were called cathode rays because they, you couldn't see them with your naked eye. They could be deflected by a magnetic field. They had electric charge, but they didn't know what they were, so they called them rays because all the rave back then was to try to describe everything in terms of a wave. And the idea that we have light rays, well, these are cathode rays. And it turns out that after more careful observation, these in fact behave far more like particles. And they were identified as being a constituent of the atom. In fact, the very first constituent of the atom that was identified, basically the first chunk of stuff, we could definitively say this is one of the building blocks of the atom, was the electron. And the first model of the atom after this was called the plum pudding model. And it was the idea that you've got basically this glob of positive charged goo with negative electrons kind of, stuck in there like raisins in a plum pudding. And something I did not realize until I got into college, because, I'm sure you heard about in high school, maybe even middle school, depending on where you went, about the different models of the atom. And they were all talking about the plum pudding model. And something I didn't realize is that all plum pudding has raisins in it. That's something, a little fact that it escaped my knowledge. I was unenlightened until I got to college before I realized or read someplace that all plum pudding had raisins. Then the model kind of made sense. And that you've got this plum pudding goo that's got an overall positive charge, and stuck in there, floating around, are little electrons. And the atom had to be electrically neutral. Since we know that the electrons were negatively charged, that means there had to be a bunch of positive charge there as well. And the first model was, well, it's in this positive goo. And the electrons are then kind of confined in there because they're surrounded by positive charges. They can be that close to each other because they're shielded from the other electrons by this positive goo that's around them. The problem is explaining atomic spectra with that model. It couldn't. Because if you imagine sticking electrons in this positive goo, you'd expect some vibrations, some oscillations, some slight interactions between electrons if they got close to each other. And they predicted what sort of energy changes they could produce. And all the models had basically a continuum of energies that should be absorbed or emitted. But that's not what was seen. We saw distinct energy lines in atomic spectra in that the emitted energy came in distinct values. And they have patterns to them. And so this model was completely inaccurate.
So basically, it didn't yield a quantized range of emissions.
Yeah, there's no way to get, as you say, quantized emissions. And Rutherford wanted to probe the distribution of electrons in this plum pudding model. And so he basically used alpha particles, which is something else that was recently discovered. I'll probably talk about this maybe even later today. But alpha particles are essentially helium nuclei, and they're emitted during radioactive decay. And so they had sources that could produce these alpha particles, which are quite massive. So, but they're also positively charged. They could be emitted easily, collimated in a beam, and would make a nice bright spot, even if a single one hit a phosphor screen if the room was dark enough. So Rutherford proceeded to torture a large number of graduate students by forcing them to sit in a dark room with a big phosphor screen and an alpha source hitting a thin piece of gold foil. Basically, gold could be hammered into incredible thinness, very, very, very thin, so that if an alpha particle went through and interacted with one of the atoms, odds are it would only interact with one atom. You wouldn't have multiple interactions. So that's why they used gold, because it was incredibly malleable, is incredibly malleable as a metal, and you can make incredibly thin sheets of gold. And so sending in positive charges into this, the expectation was there'd be slight deflections as the positively charged alpha particles went near an electron. And by looking at the angle distribution on the phosphor screen,
they could then maybe get an idea of the distribution of the electrons. Except that's not what was seen. They were seeing most of the alpha particles go straight through without any interaction, which is kind of what they're expecting. But there were many, far too many to discount statistically, that ended up going off at large angles. Instead of a teeny fraction of a tenth of a degree, which is what they're expecting, they were being deflected to 2, 3 degrees, 5 degrees, 10 degrees, and they started placing the phosphorus rings around, and they were even seeing on rare occasions complete bouncing back. Like the alpha particle would come in and interact with something so strongly it'd be reflected straight back.
Complete reversal of trajectory.
180 degrees. And Rutherford likened this to basically shooting an artillery shell. He called it what were those guns called? A 5-pounder? Yeah, because the shells weigh 5 pounds. So a 5-pound artillery piece firing a shell on a piece of tissue paper and having the shell bounce back at you. That's kind of how he described this situation, is what they observed. And thinking about this, the only conclusion you could have is that there may be electrons, floating around inside the atom, but they couldn't detect them. But what they could detect is a very teeny, incredibly teeny, very heavily positively charged nucleus. And the only explanation for this is there's something in there with positive charge that has a whole lot more mass than the alpha particle. And it's positively charged. That was the only explanation. Pretty much everybody agreed, yeah, that's the only thing that makes sense. And so the model was adjusted and called the Rutherford model, where you have a teeny positive charged nucleus, and you somehow have electrons orbiting this nucleus. They're attracted to that positive charge, confined to the atom, and we know that the electrons have energies, so they must have some sort of kinetic energy, so they must be in some sort of orbit, kind of like planets in a solar system. But there were serious problems with that. In that classically, that's impossible. Because when an electron moves in a circle or in any sort of orbit, any closed trajectory, it's accelerating. Therefore, classical theory had that anytime you get a charge accelerating or changing its direction, it's got to emit light. It's got to emit energy. And if something like this were to occur, the electrons would spiral in, losing energy constantly until they would basically collapse into the nucleus. That was the only possibility from classical physics. So yeah, you'd expect emission, but it should be continuous, and the atom should basically self-destruct. And there was still no mechanism for atomic spectra. And people said, yeah, we've got to have a positive nucleus. That means the electrons have to be moving around the nucleus for the atom to have the size we have. But we still couldn't explain spectra, and we got something that was contradictory to current theories. This was very unsatisfying. And so just to talk about the patterns we see in the spectra, and you saw the spectral lines when we had that demonstration in class. Every chemical, every element has a unique fingerprint in light. We call it spectra. But those spectral lines form patterns. In fact, if you look at the higher energy emission lines, the high energy emissions, they are all equal to sum of 2 or more lower energy emissions. So there was a pattern. And people were developing these very complex mathematical models to even predict lines that hadn't been observed. And the models actually worked on many occasions, predicting emission lines or absorption lines that hadn't been observed before. So we knew there was a pattern. The pattern was predictable. We could even predict emissions we hadn't seen before with not as careful observations. And that was clearly a clue into the nature of the atom. There's something about the atom that gives us this. And remember, Planck had the idea that black body radiation could be explained if the energy that was emitted came in chunks of teeny values of Planck's constant times the frequency. One of his first things that he expressed in the communication was a very bold statement that maybe these emissions are coming from the electrons in the atom, and that maybe the energies of the electrons are somehow restricted. And he had to backpedal off of that through a lot of pressure. I talked about that. But a fellow by the name of Bohr latched onto that idea and actually refined it to a greater degree. So his idea was actually kind of bold, saying that, well, electrons don't continuously radiate away energy and collapse to the nucleus because they can't. We don't know why, but let's just accept the fact that they can't because we don't see them doing this. Ergo, they should be confined to specific energies. And that the emissions we're seeing are when electrons go from one energy level to another. And so what we're looking at are the differences in energy levels represented by these emissions. That one idea explained the patterns that we're seeing. And there are then calculations based on what these energy levels must be for each element. And all the emission lines are explained by this simple model. For example, if we have the lowest level, call it the ground state. I'm going to call it E naught just for convenience. Sometimes this is also called the first energy level. And then you've got another level that's quite a bit higher in energy, called the first excited state, or the second energy level, and then the second excited state, third energy level, you could call it either. And basically call the energy of the levels E naught, E1, E2, E3, E4, etc. With E naught, E0 being the ground state, the absolute lowest energy that an electron can have. And so, say you can have a transition between the fourth excited state and the third excited state. The light that would be given off in that emission line would equal this difference in energy. And then you could have an emission going from the fourth, say E4 to E2, where the photon is going to have a higher energy, higher frequency, shorter wavelength, equal to this energy difference. But you'd also get a transition between E3 and E2 that's of less energy, longer wavelength. And you can have really large transitions, say going all the way from E4 to E naught or E3 to E naught. So basically, the energy emissions we see are going to be differences in the energies the electrons can have if they're confined to these levels. And this model was immensely successful in explaining atomic spectra. It still didn't explain a few things. It did not explain the splitting of levels that's observed in the presence of an electric field, in a magnetic field, or an electric field gradient. There's certain things that this could not explain, but it was a huge improvement over what was previously understood. But what was not understood is why you have these particular values of energy. That was a mystery. And this is where de Broglie came in. Remember de Broglie and the napkin in the bar I told you about yesterday? And I illustrated this before. he showed that if you can think of the electron as having a wave nature and having a wavelength, every single one of these levels that were predicted by Bohr and matched up by the atomic spectral lines can be thought of as a standing wave of the electron. So basically you can have what are called Bohr orbits of certain orbital radius, and that would correspond to basically a standing wave of the electron if its orbit, the circumference, was some multiple of a wavelength. But more fundamentally, what was observed is that if you considered the angular momentum that the electron has as being quantized, again, in chunks of Planck's constant, you get the same thing. So not only does energy seem to be quantized, but de Broglie essentially was saying that the angular momentum of the electron had to be quantized as well and only come in chunks. And so now we had, with the idea of considering that the electron might be a wave and with a corresponding wavelength, the values of these energies pop right out and match experiment exactly. That was astounding. And you had Heisenberg and Schrodinger, as I mentioned yesterday, jump on this idea wholeheartedly and start applying some pretty powerful math, the math that had been developed over centuries to describe wave phenomena, but instead applying it to electrons. And they called this wave mechanics, or what is now called quantum mechanics. Basically treat the electron as a wave, and you come up with basically a differential equation called a wave equation that you then solve, and that gives you basically a prediction of where the electron can be found, what energy it has. And what started to emerge were not these orbits that Rutherford first proposed and then were refined by Bohr, but instead a probability distribution. These were called orbitals. You can kind of imagine them as a cloud, dense where it's very likely for the electron to be found, less dense where it's less likely to be found. And these formed very distinct regions in space, defined by essentially the angular momentum of the electron. For electrons that have larger angular momenta, these orbitals would extend quite far out away from the atom in giant lobes that we call p orbitals. Energy states with low angular momentum formed essentially spherically symmetric patterns of where the electron would most likely be found, and we call those s orbitals. The reason for these letters actually come back to how people were defining the spectral lines. And so we've got a lot of baggage from when we were trying to describe something, we had no idea of what was going on. And so we talked about s orbitals, p orbitals, d orbitals, corresponding to these spectral lines that we observed. So if you've heard these battered around in chemistry, that's kind of their origin. It comes from how we started referring to spectra before we even realized what that was meaning about the energies and locations of electrons in an atom. But this is what quantum mechanics gave us. It gave us a much better picture of the atom with very, very precise predictions of where the electron could be found. But again, not a prediction of, yes, this electron at this time is going to be right here. No, more along the lines of an electron in this energy state will have this probability distribution of where it would be located. And this model also explained what was called the hyperfine splittings, the subtle splittings of energy levels when you had magnetic fields present or electric field gradients present. But more importantly, they explained all of chemistry. Because where these orbitals were and how different atoms could then bond by essentially sharing electrons, by coupling these orbitals to form bonds,
This was also something that was predicted by this quantum mechanics, and it explained all of chemistry, including bond angles and bond strength. This was absolutely incredible because to this point, chemistry was basically cataloging what was observed and making predictions on models without really having an understanding of physically what was going on to create the situation that those models could describe. And so this was incredibly successful. And I said earlier that quantum mechanics is one of the most successful theories that mankind has come up with because of its predictive power. And frankly, scientists are a little bit depressed in that as we're trying to probe our current theories for chinks, we're having a lot less luck. Basically, quantum mechanics predicts the results of experiments to a degree, to a precision that we don't have the technology to probe just yet. That's why we're constantly trying to build bigger and bigger accelerators, bigger and bigger atom smashers, things with higher energy to start to push the boundaries of our theories. So that kind of is in a broad nutshell of kind of where we are. The fact that this quantum mechanics, this quantum theory has persisted with remarkably little adjustment, serious adjustment for, well over 100 years is actually kind of remarkable. And it's given us so much stuff. Applying quantum mechanics to a lot of systems has given us semiconductor devices. It's given us lasers. It's giving us pretty much all of the devices we now have that have made our lives longer, healthier, and more enjoyable. So it's really, frankly, pretty incredible. We have a question?
Dr. Steve, will they need to know who all the scientists are
Nope.
and what they're known for on the test?
I am horrible with names, and I'm guilty of projection. So I'm not going to hold anybody responsible for dates on names. The book throws a lot of them at you. But if I say the Bohr model, I expect you to know what I'm talking about. If I talk about Rutherford scattering on a question, I expect you to know what I'm talking about. But no, I'm not going to ask you to come up with that's just something you can just get from like a Google search. No, I'm not going to ask you that. I'm going to be asking you things of like, why was the Rutherford model, why couldn't it explain atomic spectra? Or what were its limitations? What were the limitations of the Bohr model? That I could ask you. I would expect you to know what I'm talking about when I say Bohr model. Okay, let's have, the projector on. Oh,
Yeah, Vermont's there.
so once you consider this question. So the electron, there's just one, in a hydrogen atom is excited to its third excited state. Basically the fourth energy level, what I was calling E3. The question is, how many different energies of photons, these basically emission lines, can we expect to see? How many different ones? How many different energies of emissions can we see as that electron drops down to its ground state? 1, 3, 4, 5, 6, 8. Think about this for a little bit. And even drawing a picture and trying to count would be helpful. So if you can, I would encourage you to try to draw your own little energy level diagram and come up with a number. Was it that asked that question?
On Crystal's shoes.
Okay, folks, I think that's giving you enough time. Go ahead and hold up your card or type in a letter on chat. Okay, what's it look like on chat?
All Bs, and then there's one that said,
He corrected himself. He
Oh, he
meant
did?
B.
Okay.
Yeah,
okay.
so I'll be.
Okay. Could I get a volunteer? Nobody chose A, and it's not just A. It's not just one. It's got to be more than that. So can I get a volunteer to defend why B is the correct answer?
I'll go ahead and explain why I chose B.
Please do.
So since it's on the fourth energy level, and just from like lecture today, from the pictures that you drew up, and from my understanding of it, I see that there's the ground state, and since it's on the fourth level, it has 3 to go down till it gets to the ground state.
So you have ground, first, second, third. What did I say? Third excited state?
Yep.
So first excited state, second excited. So here's the electron is E naught, E1, E2, E3. So it could go to which 3? Ms. Brunger, you were saying 3?
Yes. So isn't it on the fourth energy level? Wait. So electron of hydrogen atom is excited to its it's third excited state. So it's on the fourth energy level, third excited state. Yeah.
3, 4. So fourth energy level or third excited state.
Third excited state.
So it could go like to E2, could go to E1 or to E0. Is that the 3?
Yep.
Okay. Can I get a volunteer to defend why E is correct? We also saw some folks going for E. Mr. Anderson?
Okay, so it says how many different energies of photons, so, and you said that earlier that it can jump multiple states at once, so
Yeah.
I went ahead and diagrammed this on my sheet, and the combinations I got where you could have it go from E3 to E0, from E3 to E1, from E3 to E2, from E2 to E1, from E1 to E0, and from E2 to E0. Which gives us 6, I'm assuming, unique different energy jumps you
Yeah,
can.
the energy levels get closer together as you go higher.
Mhm.
So in all atoms, the biggest energy jump is from the ground state to the first excited state.
Mhm.
So our first volunteer had this one, and this one, and this transition. No, had this transition,
I think he,
then this transition, then this transition. Okay, yeah, that's right. But you're saying that we could also have transitions between not just an excited state in the ground, but also from an excited state to one of the lower states and then to the ground.
Mhm.
Okay. Does anybody have anything else to add to here? Maybe thinking that there might be other possibilities like 8 or 5 or 4. Okay, I'd like to hear some discussion. Either unmute and just speak through the mic or type a chat. What do you think's going on here?
okay, well, you've heard my argument.
And the only thing I'm going to say is it's not A. I'm not going to dismiss any other arguments, so think about this for a bit.
say it's excited to the.
Just saying that, I'm not saying at all how it got to the third excited state, I'm saying we got an electron in the third excited state.
And what got there
Let's
is.
just ignore its provenance. Let's just say that that's what we're starting off with. The question is, given that you've got an electron in that excited state, how many possible numbers of, or different energies of emissions could we see? Or equivalently, say that we've got a billion or so atoms, and we've excited all of them to that third excited state. What energies are going to see if we look at just what sort of light comes out of the sample?
We got a couple discussions.
Okay, please read them aloud.
After the point made in the class for E makes me believe there must be more than 3 different energies of the photons. And then we had another one. Well, now I think it might be E because it's more complicated. I need to review this content though. Sounds like they're.
The most complicated answer is not always the correct one.
We got one more, Dr.
Please read it aloud.
I just thought that since the electron should be in the first ring before being excited, so exciting to its third excited state, it should be in the fourth ring, but move 3 times, thus 3 photons.
Okay, to be clear, we're talking about something decaying from the third excited state, not how it got there. So we're not concerned with how the electron got to this energy level. We're interested that given something is in that energy level, what sort of energies of photons could be emitted as it eventually finds its way back down to the ground state.
Basically, how many unique emissions we can see from it.
Yes. Okay, go ahead and hold up your cards or hit a chat letter. What's it look like on chat?
All E's, 1 B so far.
Okay, so it's we had very few E's before and lots of B's. Now we have very few B's and lots of E's. That's actually good because E is the correct answer here for exactly the reason that was stated. And so this diagram here is correct. We have 4 energy levels: first energy level, second, third, fourth, or ground state, first excited state, second excited state, third excited state. And so we're given that our electron starts in this state. So there's a number of different pathways. It could drop straight down to the ground state from there, giving off a very large energy photon. That's this first one. Or it could drop down to the first excited state, and then from there, drop down to the ground state. So with these 2 emissions. And those are 2 different energies. Or it could drop down to the second excited state, and then from there to the first excited state, and then from that state to the ground. So a 3-step decay. So it could do it all in one big chunk, in 1 step. It could do it in 2 steps. And there's a couple of possibilities for 2 steps. It could drop down to the first level and then first to ground, or to the second and then the second to ground. Those are the possible 2-step decays. Or I could do it in 1 3-step decay, where it goes to the second and then to the first and then to the ground. So the electron could either do it in 1 big step or 2 steps, and there's 2 possibilities for a 2-step. Or it could do it in a 3-step.
I'm sorry if you've already explained this, but maybe I'm still confused. How can you tell if it is a 1, 2, or 3-step? Like, what makes that difference?
By the energies, in that the energies are not evenly spaced. In all atoms and molecules, you'll always have a much bigger energy difference between the ground state and the first excited state. So the difference, the scale here is energy increasing vertically. And whenever we have atoms and molecules, the ground state is going to be the lowest energy, but the first excited state is usually quite a bit higher than the ground state. And then each successive energy level above that is a less and less of an energy change. To the point where if you start talking about the fourth energy level, it'd be about there, fifth energy level, about there, and the sixth energy level would be like less than the thickness of the chalk line. And we could have like the 30th energy level. They're measurable, they're discrete, but they get really, really, really close together. And so the differences between the energies are the clue into what these steps are. And we saw this pattern long before we had the model of atoms that we do now. This was something that was observed, and people noticed this pattern and even predicted new lines based on these sort of patterns. So these energies are all going to be different because the separation gets smaller and smaller with the higher energy you're talking about. Okay, other questions? Okay, I'd like to move on and start talking about the next chapter, getting into stuff in, chapter 33, radiation. Radiation is a scary word to many, but it's actually a fairly mundane process. We get radiation from light bulbs. We emit radiation ourselves just by the heat we give off. That's all radiation. Basically, it's light. And as we said before, there is light of very, very low energy that we can't see, thermal radiation, radiation. That's light, just as a color that we can't see. And then we have visible light. We have infrared, which is just below visible. We have the visible. Then we've got ultraviolet, which is just a little bit higher energy than what is visible. And we can talk about microwaves. We can talk about X-rays. We can talk about gamma rays. That's all light. Basically, radio and X-rays are pretty much the same thing. They're photons, they're light, but of different energies. We actually call something a radio wave or light, visible light, or ultraviolet, or infrared, or an X-ray or a gamma ray, more on how it's emitted. What is the process that emits that light, rather than what the energy is? For example, we talk about gamma rays as light that it's emitted from a nucleus due to a change in nuclear energy levels. So as nucleons change their energy, they give off gamma rays. But some of those levels are very, very close together and are in what we would normally call the X-ray range. X-rays are given off when electrons in atoms go from one level to another. So like in the hydrogen atom, technically we're talking about these photons. They are called X-rays because they're coming from electrons as they translate from one level to another in the atom. Yet there are many X-rays that are much higher energy than some gamma rays, because there are some energy levels of nucleus that are very, very close together. And so there's overlap in what we call a gamma ray, what we call an X-ray. We talk about light, the generic term light, as coming from a transition between electrons that are bound in molecules, not individual atoms, but molecules. For the most part, a lot of those transitions are in the range that's visible to us. And we talk about radio waves, for example, as being emitted by electrical currents moving in large conductors, typically. Basically, charge moving over fairly large distances. Oscillating will give us what we call radio waves. So basically, we call something a certain radiation level, from light depending on how it's, what it's coming from, and not just so much its energy range. But there are other forms of radiation. Basically, the first kind of radiation that was observed was, well, these cathode rays. And so that's what they were called. We now know that they're electrons. Basically, you had a person running a cathode ray tube, and he noticed that the photographic film he had elsewhere, even in sealed containers, sealed envelopes, was getting exposed. And these were mysterious. Basically, what sort of light was doing this, that was getting through the envelope to expose the film? This fellow was called Röntgen, was his name, and he called them X-rays. And it turned out that the cathode ray tube, the electrons, as they're accelerating and slamming into materials, are giving off these X-rays, basically light. And then you also had a fellow by the name of Becquerel, not too much later, noticed that photographic film was getting exposed when it was put next to, basically in a drawer where he had some minerals stored that contained uranium. And then a lot of people started looking at stuff and found that we could have stuff, exposed photographic film, that was naturally occurring in rocks, as well as coming off of these cathode ray tubes. And it was, I believe, Curie and Pierre that coined the term radioactivity for basically a mineral or an ore that had atoms in it that would basically emit this radiation. And we had, back then, before they knew what they were, they called these forms of radiation alpha, beta, gamma, and then X. And it turned out that the alpha particles, positive charge, heavy, basically they have mass, and they were basically turned out to be helium nuclei. Basically, as we now understand the nucleus, it's made up of protons and neutrons, and depending on the size of the nucleus, there's a region of stability where you have certain numbers of neutrons and protons. But if you've got too many protons in a nucleus for it to be stable, what you frequently do is you have the nucleus spit out an alpha particle. And that will help out the balance. And so the beta particles had a negative charge, a very low mass, and we now know that these are electrons. Basically, folks noticed that these beta particles, which is what they called this emission from certain ore, like uranium, you see beta particles from uranium, had the same properties as the cathode rays. And we eventually determined that those came from the atom. So we identified then those as electrons. But they were called beta particles and beta rays before we really understood what they were. The gamma rays also came from radioactive elements, materials. So it was a result of radioactive decay of an atom. But these particles or rays had no charge, had no mass. We now know they're essentially photons, much like the X-rays that we get from atoms. So we also know that X-rays are now essentially photons, but they come from a different source, so they're called something different. I could put a caveat here. These are all forms of what we call ionizing radiation, meaning if they hit a material, they can knock electrons out and ionize it. Basically, they can form ions when interacting with something. And that's essentially how they were all detected. They caused chemical changes in photographic film. And this gave a clue in the energies that we saw. Just like atomic spectra gave us clues about the nature of the atom. The energies and the specific particles that are emitted from the atom, from the nucleus of the atom, gave us our first clues as to the structure of the atomic nucleus. And that's a whole nother fascinating story that unfortunately we'll have to wait until next week. So this is where we'll start up with things in chapter 33 again then on Monday. Thank you for your attention. Study well for the exam. Look for that practice exam to show up as an online quiz with the Proctorio. Do try to do your homework and look at the descriptions of the Proctorio software and download that and try to get it ready because you will have to have that for the final exam. Thanks again for your attention. I'll see you on Friday.